Okay, our story so far is that we talked about computing changes in potential energy. And in particular, we have talked about potential energy as energy that an object has because of its position. And we contrasted that with kinetic energy, which is the energy that an object has because of its
height, position. Oh, kinetic.
kinetic.
What is the question?
You know, energy that an object has because of its motion. Yeah, exactly. Kinetic energy is easily computed. For any object, the kinetic energy K is equal to what?
The change in potential.
For any object, its kinetic energy K is equal to
1/2 mv squared.
1/2 mv squared. There you go. But potential energy is a little bit more complicated because it depends upon the force that is doing the work. And so each force, such as gravitational force, such as a spring force, is going to have its own associated potential that goes along with this. And so yesterday we said that the change in potential energy because of gravity is going to be mg times delta H here. Your book uses PE for potential energy. All the cool physicists use U for potential energy. You're going to see me do both. And we said that the change in potential energy starting at x equals 0 is going to be given by 1/2 k times x final squared. And if we had still other kinds of forces, they would have still other kinds of potential functions. It changes based on your force. That's exactly. It's a little annoying. It's an annoying feature about physical reality. But even with all of that annoyingness, nevertheless, we're going to find out that potential energy turns out to be really convenient way to solve problems. So don't despair, because these are actually the only two forces that we are going to commonly encounter, which is nice. Take AP Physics, we'll have better tools, we'll be able to deal with other forces. But for our purposes, there it is. Yes?
What tools would you use? Just like
Integration.
okay.
Okay, so we have this. Now what we'd like to do is to consider, this will compute changes in potential energy. We'd like to consider, can we get an actual value for an object's potential energy? And the answer is yes, but only relative to a 0 point. So let's take a look at an object of mass m that is at a height h above ground. Now, to get to that height h above ground, somebody had to carry it. And for that carry, that somebody did work. And the amount of work that they did against gravity in getting to the top was equal to mg times the change in height that we have here. Well, if my height is h, then it makes a whole lot of sense that I might call the bottom of the building y equals 0, right? And if I put this as y equals 0, then it automatically follows that the top of the building is y equals h. So that the work done against gravity, which is equal to the change in potential energy, is mg times delta h. But since the delta H is final minus initial, or H minus 0, then the change in potential energy from 0 is mgh. And what we're going to do is to arbitrarily assign when you are at the 0 point, your potential energy is 0. So I can write this as potential energy at the top minus 0. Or in other words, the potential energy at a height h is equal to mgh. This is the potential function for gravity. And what it gives us is the potential energy that an object has relative to wherever 0 is. Now I say relative to wherever 0 is, the choice of 0 is arbitrary, right? So let's put some numbers to this so we can see what's going on. In particular, if I have a 2 kilogram object and I have a 15 meter high building, so that this point is 0 and this point is 15, then the potential energy at the top of the building, U of 15, is mgh, or 2 kilograms times 10 meters per second squared, times 15 meters, or 300. What's a kilogram meter squared per second squared?
Meters per second.
No. Kilogram meter squared per second squared. It's almost a newton, but a newton is a kilogram meter per second squared. What's a kilogram meter per second squared? It's a newton meter, which is a joule. That's right. And there you go. So
What's the newton?
kilogram meter per second squared, right? Mass times acceleration.
Okay, so yeah, the second.
So then x, the additional meter, additional factor. Yep, that's right. What if I asked about the potential energy halfway down the building? Well, where is halfway down the building?
7.5.
7.5, that's right. So the potential energy at 7.5 is also mgh, but this time for h we'll use 7.5. And I think it will come as no surprise to you that that works out to 150 joules, or exactly half of what we had at the top, right? And that makes a lot of sense. All of this is relative to the bottom of the building being 0. Peter in the other class asked, well, what happens if we make the top of the building 0? Actually, I think he asked about making the middle of the building 0. Well, if the top of the building is 0, where is the bottom?
Negative.
Negative 15, that's right. And if now the potential energy at the top is 0, mg times 0, and the potential energy at a point halfway down is u of negative 7.5.
Would that be for dropping a ball?
Yes. Which gives me negative 150 joules. And our first reaction is to say, wait a second, this is all very confusing because I had one 0 point here, and I got 300 joules at the top, and I got 150 joules at the middle. And of course I have 0 joules at the bottom. But if I look at the building here, I have 0 joules at the top. I have negative 150 joules here, and if you were to do this computation, you would get negative 300 joules there. So at first it seems like this is all very arbitrary and crazy, but actually it's not so bad, because you'll notice that the differences between each of these are exactly the same no matter which 0 point I pick. What is the difference between the top and the middle? 150 joules. Whether I do it like this, or whether I do it like this. Both of these have a delta U from bottom to top of 150 joules. Does everybody see that? And it is the change in potential energy that is going to cause the change in kinetic energy. So we're actually okay with this. Let me summarize what we just talked about here. Potential energy is always relative to a 0 point.
So from now on, are we going to be using gravity as a positive value? Because
You mean G?
Yeah.
G has always been a positive value.
But okay, never mind.
The acceleration due to gravity is negative G,
But G itself is.
and G is a positive value, right?
Okay.
But the changes in potential energy are never relative to the 0 point. They are independent. Of the 0 point. Okay? Good so far? Let's change the force that we're working with and consider a spring force rather than gravity. If we consider a spring force, and we take the spring from x equals 0, and we take that all the way out to x final, then we know already that the work done in stretching that spring out is going to be 1/2 k times x final squared. That is the work done against the spring as we push in the direction, in the outwards direction. And therefore, that is the change in potential energy.
Where'd you get the formula?
We got this from area. So my spring force is kx from Hooke's law. And I'm going from 0 to x final. So the work done is the area under the curve, just like so. And that shape is a triangle, right? So the work done is the area, which is equal to 1/2 times the force up here, the final force, times the distance that we push. But the final force is equal to kx. So that when the dust settles, you get this computation over here.
What's K again?
K is the spring constant, and it tells you how stiff the spring is. A large
Oh.
value is a really stiff spring, a very small value is a
So
stiff
it's not kinetic energy.
That's right. The little lowercase k is not kinetic energy. Big uppercase k is.
Oh, okay.
That is
And
confusing.
it will be given to you, or will you have to find it somehow?
You get enough information to find it, whatever. Yeah.
Wait, what's K again?
It is called the spring constant, and it is the stiffness rating on the spring. So as I said, this is the work done against the spring here, which is the change in potential energy. And because I am going from x equals 0, which is our 0 point, therefore, this is the potential energy stored up in the spring. And here it is. The potential energy stored up in the spring at any point x is simply 1/2 kx squared. And this is the potential function for a spring. So as we see, each force has its own potential function. Gravity, mgh. Spring, 1/2 kx squared. Other forces, we don't worry about. Each force has its own potential. That's right.
What other forces are there?
The electrical force that attracts protons and electrons.
What, can you combine forces?
You can. If you do, then you would treat each potential separately and then add.
So the potential besides being like pulled or pushed or compressed or what else? You said there like electrical. Like how would electrical work on a spring? Or what?
You wouldn't think of it like that. You have an object, and you have forces acting on it. Right?
Wouldn't that just be the normal force, the weight of it?
Yeah, exactly. That's right. All those different forces.
So what if you wanted to compute something with, I don't know, like a 10 kilogram force on the spring, like not this way, but maybe this way.
Okay, is it gravity or is it some other kind of force or what?
I don't know. I just picked 10.
Okay, is it constant?
Sure.
Okay, well then the work done should just be 10 newtons times the distance, right? Force equals force times distance.
Yeah, but what if it's like on the so the spring's this way, and
Yeah.
then the weight's this way.
So actually,
When are they?
I think you're probably getting too complicated here, but if you have a bunch of forces and the object is moving in a certain direction, then work equals force times distance times the cosine of the angle between.
Which
Oh,
will be 180.
well, nothing's changed.
Yeah, nothing's changed.
For the building, for if like you're dropping a ball, if you're dropping it from 150 meters and then it goes through the ground to negative 150, what do you do?
Well, I don't
Run.
think it will go.
So, if it goes negative, it just goes negative. As we saw, potential energy can take on negative values. There's no problem.
Okay, what if you consider sea level to be 0,
Yeah, exactly. That's right. So you can
and the building is like part way up and part way below?
Exactly. And so negative potential energy is not like a mystical, magical thing that involves dark
Because it's
crystals.
just the change.
It simply means below ground. It's below zero.
Or below your reference point of 0.
Below your 0 point. That's exactly right.
And you can
Now,
change your zeros.
I want to talk about why we care about potential energy, and here's why. It's because potential energy makes problem solving really, really easy. And I want to show you how that works out.
Is that what I was asking about yesterday?
Yeah. So we're going to take our 2 kilogram ball or object at the top of a 15 meter building right here, and we're going to hold it out over the top of the building, and we're going to release it. And the question we now have is, how fast will the ball go? At the bottom.
Right before it hits the bottom?
Exactly. What is the speed of the ball right when it hits the bottom?
That's not a work thing. Isn't that just you do the gravity and the mass?
You've got a really good point. This is a fairly simple problem that I could use equations of motion on, right? Do we agree? I can do that?
Straight down.
But it's a great, because of that, it's also a great training problem to show you how potential energy makes this a pretty simple solve also.
Well, what it would be, you have potential of 300 joules at the top and a potential of 0 at the bottom.
Good. All right. So what we're going to do is exactly what she's doing, which is we're going to identify a before state, and we're going to identify an after state.
How's it going to be speed?
I have a question.
Let me talk, and then we'll take your question. And now what we're going to do is we're going to do some energy accounting. We're going to take account of the potential and the kinetic energy of the ball before and after. Hi.
Hi. This is a summary. This is what needs to be included in the inventory. Okay? That's for you. That's your packet. Got any questions, let me know.
Okay. So where was I? Yes, so potential. Before the ball falls, it has 300 joules worth of potential energy. And after the ball falls, it has 0 worth of potential energy.
And then vice versa.
Yeah.
Oh, yeah, that's what's my top.
Where did this potential energy go?
Took them there.
I claim it all becomes kinetic energy, and I'm going to prove it. We know from the work energy theorem that the work net done on the object is equal to its change in kinetic energy, right?
Yeah.
And we also know from the definition of potential energy that the work done by gravity is equal but opposite to its change in potential energy. Now, On this ball, the only force acting is the force of gravity, so the net work is the work done by gravity.
Which is,
So if I set the net work equal to the work done by gravity, I see that whatever potential energy is lost will be gained as kinetic energy. And this is called the law of conservation of mechanical energy. For any force that has a potential function, the change in kinetic will be equal but opposite to the change in potential. We like to write it like this. The change in kinetic plus the change in potential adds up to 0. Now, change in kinetic plus change in potential can also be thought of as simply the change in the quantity K plus U. And we call K plus U the total mechanical energy of our object or of our system of objects. Now, total, obviously, because we're adding up all of the different types of energy, kinetic and potential. Mechanical, because we're considering only mechanical energy, we're not considering heat energy, for example. And the conservation of mechanical energy says that for objects that have potential functions, no mechanical energy is lost. It is simply converted back and forth between potential and kinetic energy. In other words, when I total up here and here, I should get the same totals like this. So that means I can account for this. At the top, in the before state, what is the kinetic energy of the object? 0, because it's not moving. At the bottom, I don't know how fast it's moving, so I'm going to write its kinetic energy as 1/2 mv squared.
Did you say it's 300?
Yes, that's right. And in fact, I'm just about to, because now when I total it up, I total up this column to get the total energy before, and I total up this column to get the total energy after, and those two must be equal. And here I substitute my 2 kilograms for mass.
And then you can just find the velocity.
And then you can find the speed. That's right. Notice it's speed that I'm finding and not velocity.
V is, well, what,
V is speed.
Why
why did you 1/2 mv speed? Isn't that? It's part of any equation, I don't know which one it is.
Yes, kinetic energy is 1/2 mv squared.
where did it say probably how much potential energy it was?
It's said by giving us the height
All right, because then that's
and the mass.
mass times height and times gravity.
So that is the basic concept behind conservation of energy. We are going to account for all of the mechanical energy before, all of the mechanical energy after, and we're going to set them equal.
That makes all of our problems so much easier.
It makes all of your problems so much
So
easier.
could you basically, if hypothetically, solve these all like basically in your head? I mean,
Yeah.
without doing the like, you don't have to go like. How do you want us to go about solving these? Because I mean, obviously we'll have to find like the potential before and after.
Yeah.
After if it hits the bottom, it's pretty obvious. But like, do you want us to like do all the like the same?
Well, let me show you a couple of different, she asked a really good question. How should we lay out our work is really what she's asking. So let me show you a couple of ways of doing it. This is my favorite way of laying it out, and we call this a before and after chart, obvious reasons. And in the before and after chart, you're going to add up all of your potential and all of your kinetic to get your total. And same thing for after, and then you're simply going to set them equal. This is one way of laying out your work, and it's perfectly fine. What your book does, which is also fine, is it sets up conservation of energy like this. It says kinetic before I think it even uses the word before. Am I right on that? Plus potential before, and they use PE for potential energy, equals kinetic after plus potential energy after. And then they fill in each of these 4 items right here. Well, these 4 items are exactly the 4 different entries on our table, right? So it's the same computation. They're simply organizing it slightly
And you
differently.
wouldn't have to write down before
So
and
that's
after.
the law of conservation of energy.
Right, this is the law of conservation of energy. That's exactly right.
When I saw when they did a formula, it said work plus kinetic initial, potential initial equals kinetic after, potential after, heat loss.
Right, that's the general conservation of energy that includes things other than mechanical, and we'll address that one more time.
Oh, isn't that because you need energy and energy heat and stuff like that?
So you may organize your work like this, or you may organize your work like this, and I don't really care. I'm fine either way. The table makes a lot of sense, honestly. The table makes a lot of sense. Now, I want to come back and solve a similar problem. I want to consider what happens if we take our 2 kilogram mass, still at the top of a 15-meter building, but now our 15-meter building is equipped with a humongous, frictionless half pipe.
Slide.
Yeah, slide. We are going to release the object at the top of that frictionless slide, and the question is how fast will it be going when it hits the bottom? Now, in the previous problem, we could have solved it with equations of motion. We can't do that anymore. And the reason is that as this ball or object drops, if we freeze it at any moment in time and do forces on it, then we've got a normal force like this, and we have gravity like this, and we have to do components, and the components are different at each point, and so then we have to do sum of forces equals mass times acceleration, and my acceleration keeps on changing because the angle keeps on changing, so I've got to do some sort of ridiculous calculus in order to get from acceleration to speed, and it's awful. It's terrible. But if I do it with conservation of energy, watch what happens. Before, after, potential, kinetic, and total. At the top, U equals mgh, which is 300 joules. At the bottom, U equals mgh, which is 0 joules. At the top, kinetic energy is 1/2 mv squared, which is 0. At the bottom, kinetic energy is 1/2 mv squared, which is 1/2 mv squared. And so when I total it up, I get 300 equals 1/2 mv squared. No calculus required. Look at that. My velocity, my speed, not my velocity, is exactly the same. Why is my velocity not the same? It has a different direction. It's going this way instead of that way. It's exactly right.
But the half pipe has no effect on the speed.
Because it's frictionless. Because it's frictionless, it does not take any energy away from the object. Where does that energy go? It has to go into kinetic energy.
That's not for the entire trip of the ball.
Great. I'm glad you asked that question. That's right. We don't go from 0 to 17. It's 0, speed up, speed up, speed up, 17 by the time you hit the bottom.
And then for just each interval, you just would like compute it, like what the like if we wanted to know at half point what it would be.
Yeah. In fact, we can do that really easily just by adding an extra point here. If I go halfway down to 7.5, then, and let's call this point like C or something, then I can just extend my table and do kinetic and potential here, and the potential is 150, we already computed, right? And the kinetic is going to be 1/2 mvc squared. So I set the total now at C. My total is 150 worth of potential plus 1/2 mvc squared, and that equals the total right here, which is 300.
And you just subtract.
And subtract, and I get, and this is m is 2, So 1/2 2 times VC squared equals 150, and VC is therefore the square root of 150, which is going to be, well, it's going to be a little larger than 15.
No, it's not 15, it's 25.
It's 225, yeah, sorry, it's going to be a little bit larger than
12.
12.
It'd be like
Well,
12.2. 12.1.
And there you go. So we can find actually the speed at any point along here, which is pretty cool. Now the interesting thing about this is
With
that-
friction.
with friction you have to do calculus and it's ugly. You have to actually know the shape of the ramp.
We're not talking
No,
about.
okay, so I just realized that if you dropped the ball down like a frictionless, like curved ramp,
Yeah,
it would just like, it wouldn't roll at all.
it's
just
right.
so
It would
weird.
just skid down. That's exactly right.
Wait, really?
Sure. If it's frictionless, it can't grab to roll.
That'd just be so weird looking.
It would look really strange.
Is there anything,
It'd be like a hovercraft.
is there like anything, I guess it is kind of like,
Ice.
yeah, ice, but is there like any surface on which is curved slope that we could like test this theory? To see if everything's.
Not usually, no. Wet ice would be your best bet. Okay, where am I? Yes, there was something I wanted to say that is really important. Notice that the speed at the bottom here is exactly the same as the speed at the bottom for the straight fall down. However, if you were to compute the times,
Over distance.
you would find that it takes longer to get down the ramp because the distance is longer. That's exactly right. Okay.
Will we ever have to do?
No.
Distances given?
Will we ever have to use friction?
Not for something like this.
Oh, yeah.
Alright.
We should do friction and
What about
resistance.
air resistance? I will smack you.
I want to consider now what happens when instead of gravity, the force that is involved is a spring. And it turns out it's pretty easy because we're still going to use conservation of energy. So our setup is going to be this. We're going to have a plunger attached to a spring here. We're going to put on it a 2 kilogram mass. The whole thing rests on a frictionless surface.
Why have fun? I'm trying to like shoot it at a wall.
And what we're going to do is to initially start our spring at x equals 0. And then we're going to compress that spring back a certain distance, maybe negative 0.3. And I say negative because we're pushing it here to the left. We're compressing the spring. And let me actually draw our situation. Here is the compressed spring. Right? Here at x equals negative 0.3.
I have a quick question.
Let me finish the setup and then I'll take the
Okay.
question. Okay. Now, we're going to release the object, and I want everybody to visualize the object clearly. When I release the object, then the spring is going to push that object, right? But as it pushes the object, the force that the spring exerts is going to get less and less as it goes, because it's getting closer and closer to the equilibrium. When it hits x equals 0, at that point, the plunger is going to lose contact with the block, because the block is going to continue on, but now the plunger, which is attached to the spring, is going to start to get pulled back by the spring as it goes past the equilibrium point. So the important thing here is that the plunger loses contact, will only do work on the spring from x equals negative 0.3 to x equals 0. And so the question we have is, once the block reaches x equals 0, how fast will it be going? Okay, so that is the setup. Now, we are going to use conservation of energy.
What's the spring constant?
Oh yeah, we need a spring constant. Very good point. Let's make one up. Let's say that little k spring constant is 100 newtons per meter.
5 newtons per meter?
5 newtons per meter would give us a really, really slow speed. What's your question?
So the spring, I want, like, when you compress it,
Uh-huh.
doesn't it go to the point which you compressed it past 0 and then back?
Yes, it will. But it will go, once it gets past 0, it's not going to keep up with the block. The block is going to go faster than the spring after that point. Because the spring is being now pulled back by its own spring force. Whereas the block will not be.
The spring slows down after it happens.
Right, the spring begins to slow down after it passes the 0 point. It's at its max speed. And since the block is on the frictional surface, it's useful. Okay, so our before situation, before we release it, is at x equals negative 0.3. Our after situation, after we release it, will be at x equals 0. And now we can compute u, k, and total. And because we are dealing with a spring, we are going to use the potential function for a spring, which is what formula?
H squared.
1/2 kx squared. And when you plug in the numbers, 1/2 times 100 newtons per meter times 0.3 meters squared. Notice I ignore the negative sign because when I square, I'm going to get a positive value anyway. And that gives me 4.5 joules. Please notice that this 4.5 joules is substantially less energy than the object had at the top of the 15-meter building, right? Which was 300 joules. And so now, the kinetic energy before was, of course, 0 because the object was not moving before I released. And so therefore, my total energy is 4.5 joules. At x equals 0, the spring has run out of energy to get to it. There's no more accelerating. And the kinetic energy of the block is 1/2 mv squared, so that my total is now 1/2 mv squared. I set these equal because of conservation of energy. And I get a speed of 2.1 meters per second. Yes?
Is the block moving with the spring when it's compressed?
Yes.
Okay.
It loses contact right at x equals 0.
Would it even move? Well, I guess would it really even? Okay, so if the block, we're not even touching the block. If the block stays still, and you just move the spring back and let it go. Like the box is at 0 and stuff.
Yeah, so the spring will like collide with the block when it comes back, kind of a thing.
When it just goes back to.
Yeah. Then
How do you do that?
That's-
Do we ever need to do that?
yeah, you're not ever going to need to do that. And the reason that that's going to be tough is that when that collision happens, that collision will actually not conserve mechanical energy. There's going to be some energy lost. You'll hear a sound, right? And there'll also be energy lost to the spring that will be turned into thermal energy. It's a really yucky computation.
So even if it's like when you compress it and then you put it like a spring, it's like this big per se, and then you compress it to this, you put the block right here and let it go.
If it
It's still
whacks into it, that whacking loses energy.
Okay.
Yeah. So what you can guarantee is that your speed would be no bigger than your computed speed.
It's always going to be with it though. With how
Yes, yeah, that's right. So you can see that the concept of conservation of energy works equally well with springs and with gravity. And this is good news for us, because if I should try to do a Newton's law computation with the springs, then my force would be continually changing as the spring extends. And the result is that my acceleration would be continually changing, and it actually gets kind of it gets interesting. Yes.
Will we ever have to find the speed of the box after the spring starts going back?
Well, actually, since it's on a frictionless surface, once you lose contact, that thing is gonna move with a constant velocity. So yeah, you could.
What if it's not reversible?
Then friction is going to take away from this energy right here, and we'll talk about that tomorrow.